Okay, so when we left off in the last video, we were doing Bohr's model of the atom. And he was basing it on Rutherford, and he was basing it on the hydrogen atom. So we had gone through 10 or 11 of his assumptions or postulates, like that the electrons orbited in a circular fashion around the nucleus, that the electrons could only absorb and emit quanta of energies, that those quanta of energies, when they were absorbed, would jump the electron up, or when emitted, let it fall back down, that the electrons could only exist in specific orbits. They couldn't just be anywhere around the nucleus. That each orbit corresponded to a specific amount of energy, and that each orbit was a stationary state called an energy level, that we numbered with the lowest closest to the nucleus as the lowest energy level, and it was n equals 1, where the n was the principal quantum number. And when an electron was in that lowest state, when n equals 1, as for a hydrogen atom, then it was said to be in the ground state. And if it was in any orbit energy level above the n equals 1, then it was said to be in an excited state. And if an electron moved from one energy level to the other, it had to absorb if it was going up, or emit if it was going down, a photon of energy that exactly matched the difference in the energy between these two levels. And that's where we left it off. We left it off saying, so EP, the energy of the photon, has to equal the energy of the final level minus the energy of the initial, the difference between them. And of course, that's the EP is equal to HF, because it's just the energy of a photon. We said that as you go up, it's a lower, the lowest energy level is at the bottom. As you go up, it's higher. So if it's going up, EF will be bigger than EI, and this number will be positive. So whenever you get a positive EP, it means it's being absorbed and the electron's jumping up. If the electron's falling down, then the final state will be lower than the initial state. This number will be a negative. And if you get a negative on your EP, it just means the electron is falling down and emitting the photon. Okay, so that was his postulate 10 and 11. And his postulate 12, he also spent a lot of time, and I'll explain why in a few minutes, but he spent a lot of time figuring out an equation for the radius of the different orbits. So the radius of the different energy levels. And you're going to love the equation he came up with. So it's Rn, and n would be the level, like R for 1 or for 2 or for 3. So Rn is equal to h squared over 4 pi squared k m q squared. And all of these, of course, are constants, times n, the energy level, squared. So h, of course, is Planck's constant, which you know, 6.626 to the negative 34 joule seconds. Pi is pi. K is the electrostatic constant, 8.988 times 10 to the 9th newtons per meter. Now for all of you, newtons meters squared per kilogram squared. All of you who took physics 12 already, in physics 12 we round this to 9 times 10 to the 9th. But here in this constant, because these numbers are so tiny, right, to the negative 34, like rounding 8.988 up to 9 to the 9th, that's a big round. So we can't round it here. M is the mass of the electron, so 9.109 times 10 to the negative 31 kilograms. And Q is the charge on an electron, 1.602 to the negative 19 coulombs. Now you might say, do you need to put the negative in? Well, I suppose if you wanted to, you could, but it's Q squared, so it's just going to disappear anyway, so I don't tend to put it in. And then, of course, N is the energy level, so the number of the energy level. So everything in the bracket isn't going to change. Like, this is all going to be a constant, and then if you wanted to find the radius for the first level, it would just be times 1 squared. And for the fourth level, it would be everything in the bracket, which is a constant, times 4 squared, etc. Okay, so that's the R for the energy level. And then once he had this equation, so we now have two equations, he then figured out all the different energy levels for hydrogen. And he did that using, so this is his number 13. He did that using these equations and putting them together. And he found that the energy of any particular level, so e to the n, is equal to negative 2.17 times 10 to the negative 18 joules over n squared. But remember, we said that joules are a really big unit to be using here. So instead we use, and it's a much prettier number, minus 13.6 electron volts over n squared. This is, okay, so this is the one we use. Now, and it's, remember, he figured it out for hydrogen. Okay, so this will give us all the different energy levels for hydrogen. So these are the three equations then that we have. Now, all of this was wonderful and good, and people were like, wow, that's great. But they had one question, which was, why, like, this is really Rutherford's model with just a few stipulations, a few changes, and what they're like, why would this be stable when Rutherford's wasn't? Okay? And so that's really the next question we have to look at. Why is this model that looks so much like Rutherford's going to be stable when Rutherford's wasn't? And Bohr's answer was because it goes back to one of his earlier assumptions, postulates that said that electrons could only be in certain orbits of certain radii, and not others. So if this is my nucleus, then an electron could be in this orbit, or it could be in this orbit, but it couldn't be the ones in between. And it's one of the reasons why he spent so much energy and time finding the equation for the radii. Because he was saying these are the ones that are this radius work and the others don't. Well, why do they work? Well, it actually goes back to our his theory goes back to our grade 11 physics. He said the radii that work are the ones where the wavelength, the de Broglie wavelength of the electron, h over mv, where the de Broglie wavelength of the electron in this particular orbit exactly fits in, like in a whole number of wavelengths for this radius, so that it could form a standing wave. So in other words, as this electron moves around this orbit as a wave, it has to be able to fit in a perfect whole number of wavelengths in the radius. If it does that, then it creates a standing wave. Remember the standing wave that we played with in the slinkies in the hallway, where instead of the wave looking like it was moving down the slinky, it looked like it was here and then here, and that it looked like it was flipping back and forth. So if a whole number of wavelengths can fit in the radius of a given orbit, then a standing wave will be formed, and de Broglie saying when that happens, that electron won't lose energy because it's in a standing wave, and then this will be stable. So in order for that to be true, then this lambda equals h over mv has to fit into the circumference of the orbit. And that was why then he spent so much time calculating the equation to get the radii of the orbit. Okay? So that's his reasoning why this model should be stable. In real life, in reality, his model, a lot of what he said was true, but his model had 3 limitations. 3 limitations. The first limitation was, and you're not going to understand this yet because we haven't talked about it, but his first limitation was that he could not explain which spectral lines of hydrogen would be bright and which ones would be dim. And if we were in school, we would do a lab where we would heat the hydrogen gas up to the point where it gave off light, and we would look at the light that